All right, so today we're going to be looking at vector methods in 2 dimensions. This is really going to take what we did last class where we were looking at vector methods in 1 dimension, and we're really going to run with it today. So here's today's plan. So we'll start by reviewing vectors in 1 dimension from last class. We'll start with like a pretty solid example, actually, just to really make sure we've nailed this one, right? Then we'll introduce vectors in 2 dimensions. This includes breaking 2-dimensional vectors down into X and Y components. Think of an X component as like left and right, and think of a Y component as being like up and down, right? This will be really important for both physics 20 and physics 30. So this whole idea of breaking down 2D vectors really is important. We're going to really focus in on mastering this in the next couple of days. So it'll be important to take any really good notes in your printed notes today if you've got them, right? Then, of course, we're going to finish off with adding 2-dimensional non-collinear vectors today. That's just a fancy way of saying if you got a vector going like this way and then a vector going this way, how can we figure out what that resultant vector is? So if we're adding these vectors together, where did we end up? That's basically what we're getting at today. Anyway, let's start with a 1-dimensional example from last class. Here we go. So Clayton rides his unicycle to the grocery store, as people do. He travels 350 meters west to get to the store. He leaves the store and goes 200 meters east when he realizes he left his wallet at the store. He moves 62.5 meters west and then finds he just actually dropped it on the ground. Then he moves 150 meters east and stops to have a nap on the road, as people do, right? So find the displacement graphically. That's using a resultant vector, and algebraically. That's the old-fashioned way of just saying positive numbers plus negative numbers, right? Let's start with graphically. Now, I'm going to give you a little bit of a disclaimer here. When you do things graphically, it's a really good idea to have a ruler and measure things to scale, because otherwise your graphical answer with a resultant vector might end up just looking like garbage, or you might have it completely off. It is normal to screw up a graphical section. I'm going to tell you that right now. It is normal, but as long as you do your best and try to draw things to scale, you should typically be all right. Let me show you what I mean. Hopefully I'm not going to screw this one up. Let's see what we got. So first of all, 350 meters west. That's the biggest number I see here. So it's going to be the longest stretch here. If I'm going to draw that, I'm going to draw it from way over here. I don't have a straight edge, so you're going to have to forgive me. This is going to be kind of wiggly. Yeah, really wiggly here. That's what we'll call 350 meters west. Now, if you want, you can label that. Probably a really good idea, 350 meters. You don't have to say it's west because the arrow tells you it's going west. You can if you want to. It's up to you, right? So from 350 meters west, he leaves the store and goes 200 meters east. Try to draw this to scale. Again, if you have a ruler and you can somehow like, oh, okay, it's a little more than half of this, that's a good idea. I'll try to draw this to scale. I would bet if I went back 200 meters, it'll take me to about here. So why don't I just like draw 2 dots and see if I can connect them like that. There we go. That's probably about 200 meters, right? It's not perfect. It'd be better if it was perfect. But you know, I obviously don't have a ruler here. And if you don't have one, that's okay as well. Just do your best to try to draw it to scale. Now, the next movement was 62.5 meters to the west. 62.5 is like, it's not quite half of this, but it's getting there. So I'd say it's probably about like that. That would be a good estimate for 62.5. And then lastly, 150 meters to the east. 150 meters is going to be like twice as long as this, like almost exactly twice as long, I believe. Well, a little more than twice as long, to be honest. Anyway, so to draw that a little more than twice as long, I'd say it takes you to about there-ish. So that's 150 meters east, right? Now, there's no guarantee that this is all done to scale. This was just done very freehand. I could be completely off with this. We need our resultant vector, though. Remember in the last lesson, I just changed to a different color here, so I think I will do this in blue. My resultant vector is always from the tail of the first one to the tip of the last one, right? Now, don't literally do a diagonal line here because that's going to be ridiculous. You didn't move diagonally down or anything. So you just have to do it just below all these one more time. Line it up with where you started, line where you ended, and draw your arrow that way, right? Now, we don't know how long this line is, right? I have no clue. We haven't calculated it yet, right? In order to figure that out, you have to do it algebraically one way or another. The purpose of the graphical approach is just so you can visually see what's going on. Now, if you don't do it to scale, your visual representation could be completely wrong. Like maybe if you drew this wrong, maybe you went over this way, right? To the right a little bit, or I guess I should say to the east a little bit. I don't think he's actually ending up in the east, right? So that's a normal way to screw this up. And that's a really big weakness of the graphical approach. If you're wondering, algebraic approach is pretty much the only way we ever do this. The graphical approach, though, it's part of the curriculum. Don't shoot the messenger. That's all I'm saying here. Anyway, to do an algebraic approach, remember, you just pick a measurement to be positive, or I should say a direction to be positive, and a direction to be negative here. I think he's going to end up in the west. So I'm going to say all of my west numbers will be positive, but all of my east numbers are going to be negative. And then you just add them all together because they're all in the same one-dimensional direction. In other words, they're collinear. They're in the same one-dimensional direction, left or right. So let's add them up. So we'll say positive 350 minus 200, because that's negative, right? Plus 62.5, and then minus 150. Throw that in your calculator all in one go. You're going to end up actually getting positive 62.5 meters as your answer. And because that's a positive answer, that tells us it's indeed to the west, right? So my diagram, probably not too bad, right? I knew I ended up in the west. My diagram with my resultant vector here showed me that I was ending up in the west. I can already tell you one flaw in my diagram. Notice how long this arrow is here. Notice how long this arrow was over here. Those are supposed to be the same. Oops, right? In other words, that's a big weakness of a graphical approach. I didn't have a ruler. There's no way of me using a ruler when I'm writing this on a pen tablet. So I didn't have much of a choice, but just do it freehand. That's why a ruler is really important on this, but I will always be forgiving. Use an algebraic approach to confirm. And if you had a diagram that was totally off, you can correct it afterwards. Not the end of the world. Anyway, we spent longer on that than I was hoping. Let's move on to something new today. So we're going to talk today about vectors in 2 dimensions. So we're not just going left and right or up and down. We're going some diagonal measurement instead, like you can see in this picture right here. So generally, just so you're aware, in terms of communicating the direction part of it, instead of saying north or south or west or east or whatever, in terms of communicating the direction part of it, we have 2 measurement systems for 2D vectors. The first measurement system is something called a polar coordinate. This is also sometimes called a Cartesian method. All it does is it states the angle that a 2D vector is directed as if it were on a graph. So think of like math 20 or math 30, right? On a graph, you just say what angle something is going and you're good, right? So I want you to notice though that 0 degrees is on your x-axis in the positive direction and your angle just moves counterclockwise from there. So if you were going straight north or straight up, if you're looking at it from that kind of perspective, straight north, instead you'd say your angle was 90 degrees. So you could say, oh, it moved 20 meters at 90 degrees. That's a way of communicating it. It's called polar coordinates, right? This one, in this case, notice this angle is going 5 meters in a direction, because of those square brackets there, 240 degrees. That's just a way of communicating it, right? You can see it's kind of like going, if this was north, south, east, and west, you could say it's going like southwest, but it's a little bit more exact than that because you're saying, oh, 240 degrees, kind of in that southwest direction. I'm going to be honest with you. This measurement system, while it is totally valid, doesn't get used all that often. It does get used every now and then. Sometimes you will see it. The more common measurement system, because I did tell you there was 2, the more common measurement system is something called the Navigator method. This is by far the one we will use way more than the other one. How this one works is it uses something called a reference angle. For those of you who have taken Math 20-1 or even better are in Math 20-1 right now, you would realize we're talking about reference angles in class right now. And it's basically just an angle that comes down from your nearest x-axis. Now, it's a little bit different in physics, though. There's a little bit of a weird caveat with this, and I'll explain it. But basically, this reference angle just indicates an angle either north or south above an angle east or west. So both of these measurement systems are valid. Both can be used in Physics 20. But again, like I said, the Navigator method is a lot more common. Let me show you how this one works in this example. This angle just so happens to be the exact same angle from that previous question, right? Let me just like fly back a slide, right? It's 5 meters, 240 degrees. You'll notice this one is 5 meters, but instead they're saying it's 60 degrees south of west. That 60 degrees from Math 20-1 is what we call the reference angle because it's coming down from your x-axis, right? Now this part here is what always confuses people. South of west. It's typical, you don't have to do this, but it's typical to say either north or south first, and then say of either east or west. You can do it the other way though. Let me explain how this works, because some people really get mixed up on this. When I say 60 degrees south of west, really think about how that wording is. 60 degrees south of west. South of west implies you're going west, and then you're going 60 degrees south of that, right? So you're coming down or south from that straight west. The reason I'm really breaking it down is because sometimes people go, okay, is it like 60 degrees south of west? Is that like this way, or do I go south first and then go west? Because that would be like this right here. Those are not the same thing, right? The easiest way to think about this, at least in terms of what my mind always kind of works, is look at the second measurement. So west, in this case, that's where you go first, and then you go 60 degrees south of that, right? Let me do another one, just like to really drive this home. What if I said 20 degrees? I'll even flip this around. How about I say like east of south? Usually we put north or south first, but you can change it, that's fine. 20 degrees east of south. And let's also add like a measurement on that. So like 5 meters, again, just to be consistent. Well, 20 degrees east of south, think about what that means there. East of south, that kind of implies we're going south, and then we're going 20 degrees east of that. So 20 degrees east of that would be just a smidge that way. I would say that's 20 degrees east of south, right? Maybe we'll do another one just for really good measure. Again, 5 meters. How about we say 40 degrees north of west, right? 40 degrees north of west. Once again, 5 meters is the actual magnitude of our direction here. Well, think about what north of west means. If we're going north of west, that implies we're going west first, and then we're going 40 degrees north of that. So maybe somewhere around here, 40 degrees north of west. And we'll say that's a magnitude of 5 meters, right? That's how long or how far we went. Hopefully that makes sense. Every single year, this whole thing kind of like messes a lot of people up. It's one of those things that, I'm sure you're sick and tired of hearing me say this, but it's one of those things that it's easier the more you do it, right? So 60 degrees south of west, really think about what that's saying. 60 degrees south of west, you got to go west first and then south. Anyway, I'm beating this to death. Hopefully you'll get it. Anyway, two-dimensional vectors. This is where we're really going to use this here. We're going to fly with this now. So note that any two-dimensional vector is really just a left or right component. We'll call that an X, and an up and down component, which we'll call a Y combined, right? So even if you went back to this, let me erase all these other things I put on here. Even if you went back to this 5 meters, 60 degrees south of west, this arrow has like a west portion to it. That would be your X. And it also has a Y portion to it. That would be your south, right? Any two-dimensional vector has a left or right, or in other words, an east or west, and an up or down, or in other words, a north or south component. It is really important for us to break it down into these components. Or in this example, we are given those components and we can put them together to find our actual like magnitude of our resultant vector here. This is going to use a lot of trigonometry, especially trigonometry that you would have learned back in Math 10C. If you've kind of forgotten it, that's not a bad thing. I can help you with that, right? We'll just build it as we go. Let's start with this first example. What is the magnitude? In other words, like the actual like amount, how far did you go, of our resultant vector in this case? We have an X component of 9 meters to the right, and then we have a Y component of 4 meters going up. So if we're looking for the magnitude, that's like solving for how long this line is right here. Notice what kind of a triangle forms when you have a left and right component and an up and down component. It makes a sharp right angle in the corner. Hopefully you remember, when you have a right angle triangle, you can use Pythagoras in order to solve for a missing side length. The missing side length, our resultant vector in this case, is our hypotenuse. So we can solve this just by using a squared plus b squared equals c squared, where c squared is our hypotenuse, or in other words, our resultant vector. Anyway, let's give this one a try. So our x direction is 9 meters, so we'll say 9 squared, plus our y direction is 4, so 4 squared, equals, and let's just call it c squared. Doesn't matter what letter you call it, it can be whatever you want. 9 squared, of course, that's 81. 4 squared is 16. This equals c squared. 81 plus 16 is 97. So 97 equals c squared. And then we want to find what actually like the length of this is. So we have to square root this now. For those of you in Math 20 right now, we're not dealing with exact values. Again, if you're not in Math 20, you might not remember what that means. Don't worry about it. We want the actual like rounded answer here though to our 2 sig digs. So c equals the square root of 97. Remember square rooting both sides here. Square root of 97 to 2 sig digs. That gives me 9.8 meters. So of course that is a rounded answer, but that is just how physics works. We have to round to our proper number of sig digs. So 9.8 meters, that is the magnitude of our resultant vector. Second part of this question, though, is a little more dangerous. In what direction is the vector going? Now, you might be tempted just to say, oh, it's going like up of right, right? You go like right first and then up, so you'll say up of right. You got the right idea there, but remember, when we're looking for a direction, we need to be a little bit more exact. In other words, we need to figure out what this actual angle is right here. So I'll use the Greek letter theta as usual to represent an angle. Now, this is where things might be a little bit more confusing for some of you. For some of you, it might be a while since you've seen more complicated trigonometry here. But when you're solving for an angle measure in a right triangle, you have to use sine, cos, or tan. And I know we reviewed this in the very first week of school, but it's been a couple weeks since that already, so don't worry if you've forgotten this. But just remember with sine, cos, and tan, they take in an angle measurement and they spit out a ratio, in other words, a fraction, using side lengths of the triangle you've got. There's an old way of remembering what each of these trig ratios do, and that's something called SOHCAHTOA, where SO means sine is opposite over hypotenuse, cosine is adjacent over hypotenuse, and tan is opposite over adjacent. So if we look at this triangle that we have here, from the angle we're interested in, which is starting at our starting point, of course, from the angle we're interested in, we already knew the opposite side, and we also already knew the adjacent side. This is the opposite side, of course, because it comes straight across from where the angle was. The adjacent side is just the side that touches it, but isn't the hypotenuse, just so we're clear. Anyway, since we knew the opposite side and the adjacent side, from SOHCAHTOA, that tells us we should be using tan, because tan uses the opposite side and the adjacent side. So let's go with this. So tan, remember, SOHCAHTOA, sine, cos, and tan, they always need to take in an angle. So we'll say tan of our angle. We don't know what that angle is, so we'll just put it there. Tan of our angle equals the opposite side, which is 4.0, divided by the adjacent side, which is 9.0. Now, the real question is here, though, how do we get that angle out of here, right? We want to solve for the angle. Well, tan is holding up that angle, right? Tan's holding the angle hostage here. We got to get rid of tan. To get rid of tan, you might be tempted to just say, oh, divide by tan on both sides. It doesn't work that way. Tan's a function. Good news is there is a relatively easy way of doing this. You just need to take the inverse tan, tan -1, of both sides. On your calculator, especially if you have a TI-83 or TI-84, on your calculator, the tan -1 button will just be accessed by pressing second, which is that button kind of in the top left corner, and then pressing 10, which is just a couple buttons above the 9 button, right? So if you take tan -1 and then type into that 4 divided by 9, and you can just put it right in the brackets that form, 4 divided by 9, and then close the bracket there, you should get as an answer theta equals, and we just want 2 sig digs here, so 24 degrees. Side note, and I can't believe I didn't mention this before we even started, I apologize. Side note, if you didn't get 24 degrees in your calculator when you just did that, make sure that your calculator is in the right mode. There's 2 different angle modes in calculators. There's something called degree and there's something called radian. We don't use radians in this course. Radians are only used in Math 30. But if you press the mode button, which is right near second on your calculator, one of the first things on that list that comes up, it says radian and degree. Just use your arrow keys to go down and change it into degree mode if it wasn't already. And even if you didn't test this, you really want to like go in and make sure that you're in degree mode, because otherwise you're going to have a very bad time. Anyway, long story short on this question, I swear most of them won't take this long. Long story short, if we were to express this resultant vector, we could say it was 9.8 meters, and then use our square brackets for our direction. The direction would be 24 degrees. And notice we went right and then we went up. So it would be 24 degrees, and I know how backwards this is, but up of right. You went right first and then up. So you went up of right, 24 degrees up of right. It's backwards, but that's just how it works. And if you really sound it out, it should make more sense if you think about what it's saying. 24 degrees up of right. If you prefer to call this north of east, that works as well. We weren't very clear on this one, whether you're up or east or north or whatever. But I would say just because it wasn't specific, I just call it up of right. Anyway, let's keep going. So now we want to focus on breaking down two-dimensional vectors, right? The last example, we put them together, the x and the y component, we put them together to get a resultant vector. In this question, we want to take a resultant vector, which it gave to us, and actually break it down into x and y components. Believe me when I say this is actually going to be a really, really, really important concept, even just in the coming days, because these are the components that we'll actually usually be putting into our calculations. The resultant vector, when it's going at like some angle in some diagonal direction, isn't super useful when we use our kinematics equations, for instance. I'll explain why when we get to that. Today, we're just going to focus on building or breaking down these 2D vectors. But let's see an example here of how we can break one down. Find the x and y components in this example. We have 12.0 meters at an angle of 50 degrees north of east. We want to break this down into our x and our y component. We can clearly see our x component is going to the east and our y component is going to the north, but we just don't know what the magnitude of those are. Well, here's what we got to do. You might be tempted to use Pythagoras, but unfortunately, Pythagoras only works if you already know 2 out of the 3 side lengths. Unfortunately, we only know 1 of the side lengths. So what we have to do is we have to come back to SOHCAHTOA and see what we can do to break down or find a missing side length. I'm going to focus on x first, right? Notice that x is your adjacent side compared to the angle it gave. Also notice that your y is your opposite side compared to the angle you gave. Now, we will not be able to use tan because we don't know either the opposite or the adjacent side, so we don't have anything useful to put in there. We do, however, know our hypotenuse. And since, well, if we're going to focus on x first, since we're looking for our adjacent side, we know our angle and we know our hypotenuse. That implies that we can use cosine, because cosine is your adjacent side divided by your hypotenuse. Let me show you what I mean. Use cosine, so cosine, now it needs to take in an angle. We just so happen to know what that angle is, so it's cosine 50 degrees, equals from SOHCAHTOA, your adjacent side, which is x, over your hypotenuse, which is 12.0. We want to solve for x. Now here's the nice thing about this. To solve for x, notice x is just being divided by 12. You literally can just multiply by 12 on both sides of this equation. So you can have 12.0 times sine 50 equals x. As long as you're in degree mode, you can throw that in your calculator and you'll have no problem at all. So let me throw this in my calculator right now. 12.0 times sine of, oh, sorry, sine. I wrote sine. Oh my goodness, you guys are probably like going, what on earth are you talking about? Cosine of 50. My mistake, guys. Good thing I caught myself. 12 times cosine of 50. That is going to equal, and how many sig digs we want? Looks like, unfortunately, just 2 sig digs. X is going to equal 7.7 meters, right? There is our X component. Now you could say 7.7 meters east. To me, I think that's a little redundant. I think it's pretty clear in the question. Up to you. Now let's focus on Y. You might be thinking right now, oh, now we know 2 side lengths, we can use Pythagoras. And you'd be right, but I wouldn't recommend it because when you use Pythagoras, you'd want to like use as many decimals on your X as possible, and we just rounded it. And that's kind of not ideal. So instead, let's pretend we didn't find X. Let's just pretend we just don't know it. And instead, let's focus on our opposite and our hypotenuse. Well, the trig ratio that uses opposite and hypotenuse, that would be your sine, because SOHCAHTOA, so is opposite over hypotenuse. So sine of an angle, sine of 50, equals the opposite side length, which is y, divided by your hypotenuse, which is 12.0. Notice this is like pretty much the exact same thing as that last one, right? Except we're using sine instead of cosine. For real this time, right? We're using sine, right? Anyway, multiply by 12 on both sides. 12.0 times sine 50 equals y. Throw that in your calculator, 12.0 times sine of 50. And round to 2 sig digs here, we've got y equals 9.2 meters. And then if you want, you can throw in north, even though that seems pretty obvious in this case. It's up to you. Probably a good idea, though, I'll be honest. So anyway, that was actually, I think, honestly, maybe a little simpler than combining x and y components to make a resultant. But still, that's pretty much all there is to it. You just have to really have a good idea of how to use not only Pythagoras, like in that last example, but even more important, a good idea of SOHCAHTOA. Now, I'm pretty sure in the classroom, you guys will be able to test if you're watching this in the classroom right now. I'm pretty sure in the classroom I have a SOHCAHTOA poster over by the door. Feel free to use that, of course. But SOHCAHTOA is a really good way of remembering which trig ratio does what. Just always remember, trig ratios need to take in an angle. So it's sine of 50. Sine, cosine, tan don't just exist on their own. They don't just float, right? They have to take in an angle number, okay? Anyway, here's another example. This time I didn't give you guys a picture. That's all right, though. We'll have to be able to construct this ourselves. Suppose Isaiah has walked a final displacement of 350 meters at an angle of 15 degrees south of west. How far west did he walk? Let's start by drawing a picture here. 350 meters, that's his magnitude, at an angle of 15 degrees south of west. Remember how backwards this is. I would recommend going west first and then going 15 degrees south of that. So let's draw this. If we're going to go west, I'll even just do a dotted line here. Going west, we're going this way. There we go. And then we're going 15 degrees south of that. That's not very much, right? So just a little bit south of that. So maybe about like to there. That might even be an exaggeration. So if we draw that with a resultant vector now, how about I change to a different color? I'll go back to red here. Our resultant vector from the start of the first one to the end of the last one is like this, okay? And we know that distance is 350 meters at an angle of 15 degrees south of west. Some of you might be shaking your head at the fact that I really break this down, but believe me, some people really get confused at this whole south of west business, right? And it is kind of tough, right? So it is important to really think about it and break it down. 15 degrees south of west. I'm really going to beat that in, okay? Anyway, the question is asking though, how far west did he walk? Remember that any two-dimensional vector, any diagonal, can be broken down into an x component and a y component, you know, left or right and an up and down, right? What this is asking is, since it's asking how far west did he walk, it's looking for the x component. We want to know how far to the x direction, in other words, west, did Isaiah walk. So think about this as a right triangle, just like before. The right angle's in the corner here. That means your 350 meters is your hypotenuse. Think about what kind of side the x is compared to the angle that you know. It is not our opposite side, which kind of narrows it down. It must be our adjacent side. So we're looking for our adjacent side here. We know our angle and we know our hypotenuse. Think of SOHCAHTOA. Think in your head right now, which of these three do you think we're going to have to use? We're looking for adjacent. We have the hypotenuse. The one that has adjacent and hypotenuse in it, that would be cosine, right? So break it down. Cosine needs an angle, so 15 degrees equals the adjacent side, which is x, divided by the hypotenuse, which is 350. We want to get x all by itself. Let's multiply by 350 on both sides. So 350 times cosine 15 equals x. Throw that in your calculator, 350 times cosine 15. And it looks, shoot, they only want 2 sig digs. It looks like we only got 2 sig digs here. Darn. The answer I got, I'll do it with 3 sig digs at first. I got 338 meters. But if you want 2 sig digs with that, remember, you just want the first 2 digits, but unfortunately, that's going to have to round up. It's going to be x equals 3.4 times 10 to the 2, because there was 2 decimal places here. 3.4 times 10 to the 2 meters to the west. That would be your answer for that first question. That's annoying when you have to use scientific notation for a number like that, but it is what it is, right? If I said 15.0, we would have been laughing because that would have been 3 sig digs. Anyway, next question. How far south did he walk? That's our y direction in this case. And notice y would be the opposite side of this triangle. Having a picture really helps if you didn't already put that together, right? So opposite and hypotenuse, we're going to have to use sine this time around. So sine of 15 equals y over 350. Multiply by 350, of course, 350 times sine 15 equals y. Throw that in your calculator, 350 times sine 15. We just want 2 sig digs. In this case, it's a little bit better. That number is going to round up to 91 meters south. So y equals 91 meters to the south. There you are, right? There might be some applications for this in terms of just like, oh, how far west and how far south did you go? The applications we're really going to get in with this is when we start using kinematics equations. With kinematics equations, you cannot use resultant vectors except for in very, very specific situations. You will need to learn how to break it down to x and y components. So the last thing we got here, at least I believe, yeah, last thing with an example, adding 2 non-collinear 2D vectors together. Non-collinear just means they're not in the same kind of direction. So in other words, they're just 2 2D vectors. You don't have to worry about that non-collinear term, right? There's some steps to this. So if we had an example like this, I didn't throw any numbers in here on purpose, just to give you a conceptual idea. If we had some like 2-dimensional vector going this way, and then from there we went some other 2-dimensional vector some other way, some other dimension with this, right? We can add these together to get an overall final resultant vector from the start of the first one to the end of the last one. So something like that, right? We want to figure out what that resultant vector is. Here's how you do it. First things first, I'll erase that. First things first, determine your x and y components of each vector you were given. So we can call this x1, and this one's x2, and this one we can call y1, and this one we can call y2, right? Find all of those. I know how much of a pain that's going to be. Believe me, it's going to take a while, but calculate them anyway. Step 2, add the x components and the y components separately. So get your x1 and add it with your x2. Notice what that would do is it would just make a super long, you can call it x3. That was really horrible that I had a dip there, but you can call it like x3. It's like a super long one. Keep in mind directions. If one of them was going to the east and then the other one turnaround was going to the west, you just have to say one of them was positive and one of them was negative, right? Just take account for that, right? But you add them together. Same with your y directions. Notice y1 is this tall plus y2. You add them together, you can make a y3, right? It's just y1 added with y2 to make a super long line. That's the whole idea, right? Then you combine the total x and y components, that y or x3 and y3, right? Combine that total into a single resultant vector as if they were perpendicular. So in other words, as if they were one big triangle, just like I did before there, right? You have a big right triangle and then go to town on that. Much easier to see with an example, but believe me, buckle up. This is going to take a little while. Good news is this is our last example. This has already been a long lesson. I apologize. Here's the example. A cross-country skier traveled 150 meters at 40 degrees south of west, and then 250 meters at 65 degrees east of south. Determine her resultant displacement. Much easier if we start with a picture. Try to do the picture as much to scale as you can. There's no guarantee I'm going to get this right on the first go. If I goof up, that is fine, right? We can always use our calculations to back us up here. Anyway, 150 meters, 40 degrees south of west. Remember, south of west, go west first. So I'm going to start right here, we'll say. We'll go west first. And then we're going to go 40 degrees south of that. That's a pretty good measurement. So I'd say it's about there. Draw the angle. There it is. We'll say that's 40 degrees. Technically, we have a right angle right there. And I'll even label this 150 meters. Good. Now, from that point, we're going 250 meters. 250 meters, 65 degrees east of south. East of south. Think about what that means. That means we're going to go south first, and then we're going to go 65 degrees. That's a pretty big angle, 65 degrees east of that, 250 meters. So it's going to be much longer than that line there. 65 degrees is a pretty crazy angle, and notice it's going to be this way, 65 degrees east of south. So I think that is probably a pretty safe estimate right there. If you have a ruler, and even better, a protractor, that can really help. But we'll say that's 65 degrees, and that's east. East is to the right, of course, east of south. And this is a much longer line than I did in the first place. So we'll say that's 250 meters. There is no way that's exact. No way at all, right? But it does give me a pretty good idea. I feel, just from the diagram I did, one thing we know for certain is that she's gone to the south, but I also have an intuitive feeling that she's probably ending up a little bit to the east compared to where she started, right? Ultimately, what we're trying to do is trying to get a resultant vector. So from the beginning to the end, how did she get there, right? The only way we can calculate this directly is finding the x components. So how far, in my mind, I think she's going east. How far east did she go? And then how far south did she go? We definitely know she went south, right? Anyway, let's break this down. I'm going to change to a third color here so I can show that work separately. Let's use green. Notice in our first vector, right up here at the top, we have an x component, I'll call it x1, and we have a y component, I'll call it y1. Then notice in our second vector, where we went 65 degrees east of south, we have an x component. X is left and right, so that's down here. We'll call that x2. And we have a y component. We'll call that y2. We just need to figure out all of these x and y components and add them together accordingly. Let's just start with x1. Notice in this right triangle that we got up here, x1 is our adjacent side. I'll even write that, adjacent side, and we know our hypotenuse. From SOHCAHTOA, the one that uses adjacent and hypotenuse is going to be cosine. So let's use cosine of 40 degrees equals our adjacent side, which is x1, over our hypotenuse, which is 150. Hopefully you can see, I won't write it down, but hopefully you can see we're going to go 150 times cosine 40. Because this is not our final answer, I'm not going to round to the proper number of sig digs here. I'm going to keep it like a relatively good decimal here. So I'm going to write this as x1 equals 114.907, we'll say. That's probably a good enough number to round it to, right? 114.907 meters, and that is to the west. Keep the direction in mind. Very, very important. Next one I'm going to find, you know what, I'll put a box around this too, just so I don't lose this answer. Next one I'm going to find is I'm going to find y1. Notice y1 is your opposite side here. Opposite and hypotenuse is going to be sine, right? So we'll say sine 40 equals y1 over 150. Once again, multiply by 150 on both sides. So 150 times sine 40. Keep as many decimals as you feel comfortable with. Y1 is going to equal 96.418, we'll say, meters to the south. Okay, and I'll put a box around that so I don't lose that either. Let's move on to our other triangle. We need x2 and y2. Let's start with x2. Notice x2 in this triangle is opposite from that 65 degrees. So x2 is our opposite side, which means y2 is our adjacent side. Okay, think about it geometrically, right? So x2 is our opposite side. We have a hypotenuse of 250. Opposite and hypotenuse is going to be sine. So we're going to say sine of, not 40, sine of 65 equals x2 over 250. x2 is your opposite, 250 is your hypotenuse. Multiply by 250 on both sides, so 250 times sine 65. You're going to get x2 equals 226.577 meters, and notice this time that's to the east. So I'm going to pause kind of right there. Notice we went further east than we went west. So my intuition in my drawing was actually correct. We did go further east than we went west. That's good to know. Now we want to find y2, of course. y2 is our adjacent side. Adjacent and hypotenuse are going to use cosine. So cosine 65 equals y2, that's your adjacent side, over hypotenuse, which is 250. Multiply by 250 on both sides. So 250 times cosine 65. This gives me y2 equals 105.655 meters to the south. Whew, okay. Let's close this off now. Believe it or not, as much work as we've just put in here, we're actually almost done. So the final step here is combine your x components and your y components together to make one triangle. We'll call it x3, that's a 3, x3, and y3. x3 is just going to be x1 plus x2, but just keep in mind those are in opposite directions. x2 is a bigger number and it's going east, so I'm going to call that one positive, and I'll call x1 negative. So for x3 is going to equal x2, which is 226.577 minus 114.907. This is going to give me, hold on, 226.577 minus 114 plus 907 or minus 907. There we go. Okay, so that's going to give me 111.67 meters, and that is going to the east. Really important number right there. I'll put a box around that one too. The other number I need to find is y3. This one will be a little easier. Y3 is just going to be y1 plus y2, and they're both south. They're both in the same direction, so I can just straight up add them together. So 96.418 plus 105.655. This is going to give me y3 equals, just throw this in a calculator quick. That is going to give me 202.073. Okay, all right, so we're almost there now. What we got to do with this x3 and y3 is we now have to combine it together to find our hypotenuse. Here's what's nice about this. Since we know both sides of this triangle, we can just use Pythagoras to find that amount. So using Pythagoras, we have our a squared and our b squared. It's going to equal our c squared, which is the length of this resultant vector, this diagonal big blue arrow that I just drew over here. So we'll do 111.67. There's a point there, 111.67 squared plus 202.073 squared. And that's going to equal c squared, where c squared is our hypotenuse here. So 111.67 squared plus 202.073 squared. Take that answer and square root it. I'm doing it all in one go just so we can save a little room here. And I will round this to my 2 sig digs, I guess, in this case, because these are supposed to technically count, these angle measurements. So to 2 sig digs, I've got 230. So you know what there? C equals 2.3 times 10 to the 2 meters. Bad news here. We found our magnitude. It's asking for a displacement. We still need a direction. Yeah, believe me. So direction is just the angle from where you started to where you ended. That's this right here. What I want you to notice is it's like it went east and then went south. So we know it's going to be south of east. We just need to calculate what that angle is. Let's use one of our trig ratios here. We know how long y3 is. We know how long x3 is. y3 is an opposite side. x3 is an adjacent side. That means we can use tan. So tan of our angle is this right here, is equal to the opposite side, which is 202.073, divided by the adjacent side, which is 111.67. Use inverse tan to get that all by itself. Here we go, 202.073 divided by 111.67. Throw that into inverse tan, and you get an angle of 61 degrees. I warned you that this is going to be a long one, told you. Anyway, so to finalize this whole thing, we are done now, believe me. Our resultant displacement is 2.3 times 10 to the 2 meters, and then in square brackets, 61 degrees south of east. And put a big box around that, put some stars by it if you want. Be happy, be proud of that answer. Holy smokes, that was a lot of work, but we managed to clear it. So I think that was the longest video of my entire life, but you guys do need some practice. And if you haven't already taken one, you guys need a break. If you're thinking of dropping physics right now, please don't. We'll get a lot of practice at this. Don't you worry. I know it seems like a lot, but the good news is those kind of questions I expect to take like 15 to 20 minutes on a test. So you'd only be given maybe 1 or 2 of them tops. We will get lots and lots of practice at this. It's just a matter of using Pythagoras and SOHCAHTOA. And then it's a metric ton of work in between. Anyway, try that linear and collinear vectors handout. We basically need to have this mastered before we move on. Best of luck, guys.